Today we're going to continue on with the kinetic molecular theory, but we're only going to talk about gases for this unit and the next unit. And this unit actually builds up to the next unit when we start talking about Dalton's law of partial pressures and Charles and Doyle and Avogadro's principle. So this is kind of the lead into the next unit, which is kind of nice. Again, we talked about gases last topic. We didn't talk about them as much as the solids and liquids, but we're definitely going to talk only about gases for the next two units. One thing in particular, gases, they move around in a very random fashion. There's no predictable pattern of which way they're going to go. A cool fact. All gases, no matter if it's light hydrogen or super heavy radon or a combination of elements that make up a really heavy gas, if you had 1 mole of particles of any gas at the same temperature and same pressure, you will have the same volume. Now, do you remember, I think it was Unit 4, we talked about a certain condition at STP. What's STP again? Standard temperature and pressure. That if you had at STP 1 mole of any gas, does anybody remember what volume that was? Look at that. 22.4 liters. Now, the thing is, that'll always be given to you. I mean, that's not something that you have to memorize. But it's nice to know it. It is nice to know, so that's a good piece of trivia. And the key thing here is, it doesn't matter if it's this really heavy gas or really light gas. Any gas, okay, 1 mole of any gas will occupy the same volume if we're at the same temperature and pressure. However, this is a standard set of conditions, which is kind of nice. All right. Don't forget this number, Avogadro's number, 6.02 times 10 to 23. I'm sure we're going to use that number sometime soon. That's right. Yeah, it's still there. Yeah. Oh. I had no idea what that was. All right. One important thing to remember about gases, unlike solids, unlike liquids, gases are made up mostly of empty space. In other words, that's why I can see all of you. And versus if we were in a swimming pool, you'd be a little bit bored because of all those particles that are in the way. But a gas is made up mostly of empty space. So that's one really cool feature about it. A gas is very compressible, so we can compress a gas and change it into another state. That's the only phase that we can compress and change into another state, which is kind of nice. Temperature. Temperature is related to how fast gas particles will move, and also related to the type of pressure that it'll have. I like using this analogy of ping pong balls. So if I have this box, okay, I have a box, and it's about yay big, and I've got maybe 10 ping pong balls in there. And when I shake it rather slowly, that means we're at a low temperature. So could you imagine the ping pong balls kind of like bouncing around, just ever nonchalantly, or nonchalantly actually. Okay, I've got a cold, so I'm having fun trying to pronounce things. So, and that's a low temperature. Now, as I increase the temperature, what happens to those balls in the ping pong box? Or in the box? They start going fast, colliding into each other, colliding on the sides, so they start going crazy. So, when we talk about how fast a gas particle is moving, we want to look at its temperature. The lower the temperature, the slower they'll move. So, riddle me this. If the temperature gets to a certain temperature, is it possible that I can get those balls to stop? Yeah. There's a term called absolute zero, which we'll get to a little bit later on. Sounds familiar. Question number 22 on the test yesterday that I gave you the answer to. It was the one that was highlighted or boxed.
It was letter D.
D, yes. Wow. Okay, so when we talk about pressure, okay, in chemistry we talk about pressure. In physics, you'll talk about force. Okay, so like for example, Gravity is something that we associate with force. In other words, all of us are experiencing, depending on your mass, my force due to Earth is the same whether I'm standing or if I'm laying down. True? Yeah. I mean, force is based on gravity and your mass. However, pressure is a little bit different. So if you're going to do push-ups, normally we do push-ups with our palms down. But if you're a real man, you'll do it fingertips. Okay? Fingertip push-ups, right? I mean, there's no other way. Pinky, my bad. My pinky. Yeah. Oh, yeah, I don't want anybody to get hurt. So we won't do that. But when we talk about pressure, pressure is determined by the surface area. So if I look at my palm, yeah, I'm a big boy, but my palm can handle all this mass. However, fingertips, that's really tiny compared to the surface area. Kind of like, here's another horrible image that I don't really want to put into your head, but the stilettos, you know, those little high heel things that are like this big and have a little tiny heel. If you put me in a pair of those and I start walking around, I'm going to be punching holes in the floor. Yeah, because, again, you've got all this weight, about 230 right now. So 230 pounds on that little itty-bitty spot, just boom, boom, it'll be punching holes. Thank you. I appreciate that. Don't be negative. All right, so that's the difference between force and pressure. Yes?
My keyboard is being kind of whacked.
All right, so
It's not working.
don't use it. Yeah.
Just take it off, restart it, and put it back on.
Don't do that. All right. Pressure also determines on how many strikes you have. So, like, those of you who drive, you might know what this is. In other words, I'm sorry, I didn't finish it. PSI. Does anybody know what PSI is?
Square inch.
Pounds per square inch. So normally, and again, I have the low end tires. My ideal pressure is 32 pounds, 32 PSI. Now, what that means is, as I look at a gas particle, just went by. What's the pressure of that gas particle as it goes by? 0. It's not until it hits something that there's a pressure. Okay. The atmosphere right now, the gas particles that are hitting us in the eye right now, bouncing off my glasses and then hitting my eye, it's striking and making contact. As the gas particle passes by, there's no pressure until it hits something. So the increased number of collisions that we have there, that increases the pressure. So as you increase the temperature, you're going to increase the number of collisions. Also, you have more particles in your tire. Like if your tire gets low, what do? Put more air in it. Very good. So we're actually occupying more gas in that same volume. So if you occupy more gas in that same volume, then that pressure is going to get greater because they're colliding into each other as well as the wall. So when we talk about pressure, the number of collisions, it's all about the collisions, and we can increase the collisions by either increasing the number of particles or increasing the temperature. Pretty cool. So again, there is a relationship between pressure and temperature. We'll talk about that here shortly. Let's see, what else do I want to talk about there? Okay. Barometer. There's a lovely picture of a barometer from back in the day. And we don't get to use these anymore. They're not safe. It's not safe to be around open containers of mercury. They do cause some neurological damage, but I mean, that's superficial. But here's how the barometer in this case works. You've got a glass tube that's open on one end, closed on the other. So you fill it up with mercury, put your finger on the end, invert it into the pool of mercury, take your finger out, lick it off. And then what happens is the mercury drops. Okay? So as it drops due to its own mass, because mercury is pretty heavy, you're actually forming what's called a vacuum. What's a vacuum? Hush. What's a vacuum? He likes talking about the same thing over and over. What's a vacuum? There's nothing. Nothing. There's no air. There's no any gases whatsoever. So that allows for that substance to move up and down rather easily. Okay. So when the atmospheric pressure is high, like today, we've got all the windows closed because it's so sunny out and there's very few clouds. The atmosphere is pushing down on the mercury, causing the mercury to rise. So higher barometric pressure means beautiful days. If it's stormy out, water weighs less than nitrogen, so there isn't as much pushing down on it. so the mercury will then drop. So a lower barometric pressure means that we've got storms. Higher means beautiful day. Okay, that was back in the day. Now we have better technology. These are the conversions that we'll be using for the next day or two, especially for your homework tonight. I went ahead and highlighted this because I like using that conversion. I don't know why it's not in the table, but I just didn't put it in there. These are all acceptable. You'll be given access to these conversions. It doesn't matter if you want to use the pascals, kilopascals to atmosphere, or 1 atmosphere for kilopascal. It doesn't matter. You'll have it. Just make sure you're using the correct number with the correct unit. Now, anybody see Tangled? The little lizard thingy. Somebody last year made that for me. It has kilo above it, and that character's name is Pascal. That's finally might make a little more sense now. So a kilopascal is that pressure unit. Now, what's that? Huh? Okay. What? He doesn't get it. It's still the mercury in the fish. Good. So let's do some conversions, and again, you'll have access to these units. Now, again, when you get to the homework, you may have to scroll up to see them again, so I apologize for that. Oh, I know, the labor. All right, so let's look at the first. Says, when reading the classroom barometer, you find the mercury has risen to a height of 72.9 centimeters. What is the value expressed in kilopascals and atmospheres? Actually, we'll do kilopascals here, atmospheres here. All right, so if you're in, again, the centimeters of mercury is actually a pressure unit. It's not an annoyance saying, oh, we got centimeters. Yeah, we do, but it's a unit, actually. So, good old factor labeling. Start with what you know. And what do you want to convert that to? We want to get it to kilopascals, but do we have a conversion that will get us from centimeters of mercury to kilopascals? Do we have something? Millimeters, very good. So we have this conversion here. So let your units tell you how to get there. So again, we're going to go from centimeters of mercury to millimeters of mercury. Which one is bigger? Which one's bigger, centimeter or millimeter? Centimeter. So assign the value that's larger, 1. How many millimeters in a centimeter? 10. Very good. Or 10 to the 1. Okay. Tomato, tomato. So now we have our millimeters of mercury, so we want to get rid of that, and we do have a conversion that will get us to kilopascals. So we'll put millimeters of mercury here, and kilopascals there. And from your table, who gets the 1 here? Kilopascal. It's right there. So you'll give your 1 there and 7.501 there. I love colds. I love them. I love having phlegm and snot and everything. It's awesome. So yummy. They're chewy sometimes too. Sorry. Sharing my personal experiences. Probably not a good thing. All right. Questions on that? Let's do another one. Gone. And I don't know what this means down here. This. I don't know what that link there is, but yeah, if you need to see it again for whatever reason. I don't know. All right, let's look at this one. So now we're going from millimeters of mercury to atmospheres. No, it's not. Whoop. Thinking of milliliters. I don't want to go to milliliters. A millimeter. So we want to get rid of millimeters of mercury. What do we want to convert the millimeters of mercury to? Kilopascal, good. And just like what we did in the last one, so that. Now you have an option here, whether you want to use, this one here or the one that I have highlighted. And it doesn't matter, just as long as you put the appropriate number with the unit. Okay. This is the inverted value of the 101.325. And if you don't believe it, do 1 divided by 101.325. It'll give you something very close to that. Okay. Which one? The one on the table? Okay. Let's scoot that up. And again, if you don't want to use the one that's in the table, then go ahead and use the 101. I'm going to go ahead and use the 0.9869 ATM or 1 kilopascal. Okay. Or tomato. If you want to go 1 atmosphere was equal to 101, 101, 325 kPa. In other words, I'm substituting this for that, or in this for that. So the greens would be your substitution for the blues in that section, if you chose to do that. It's still going to give you the same answer, hopefully. And that answer was what? 701, and that is an atmosphere. So again, it doesn't matter which conversion you use, but don't get crazy and go, well, I'm going to use 0.009869 for 101.325 kPa. That'd be bad. I'm sure it's you didn't use parentheses.
I put the 101 still on the top.
Good old factor labeling. Never lose sight of it. It's our friend. It's our buddy. It's our pal. All right. All right. Now it's going to get tough. Pay attention. Hey, green lines? What do you mean? Oh, I don't know. Embrace the green lines. Be happy for them. All right, so we are going to embark on a new temperature scale. You've heard of Fahrenheit, which all the ding-dongs in America use. We talk about degrees Celsius, which the rest of the world uses. Today we're going to talk about the Kelvin scale, which is what we must use when we're working with gases. Okay, absolute zero, there it is. Absolute zero is as cold can get. Okay. Absolute zero is when all heat has been removed. Take it away. That's when all particles stop moving. This desk. Oh, yeah. Oh, yeah. This desk is moving like crazy. I mean, it's driving me nuts how much it's moving around. So if I try to hold it down, have I made the situation better or worse? Worse. Why? Because I'm heating it up. Yeah, so I'm making it even worse because I'm heating it up. So if I want to make it better, I'm going to throw it outside where it was cold this morning, or the absence of heat. Yeah, it'd be a cold burn. Yeah. That's not absolute zero, but it's cold. Oh, sorry. All right, so nowhere. It's in deep space.
Deep space?
Deeper. Okay. Deeper.
How do you know it's
Deeper.
No one's been to Pluto.
Deeper.
Deeper than our galaxy.
Deeper. They have tried, and they've gotten within, I think, 1 Kelvin of it. But it's really tough to get rid of energy, especially when we have so much around us. There's a lot of energy in this room. Yeah. All right, so when we talk about the actual temperature, it's this, negative 273.15 degrees Celsius, but we dropped the 0.15. We don't care. I mean, if you're a nerd, you can leave it on there, I guess. But the reason why we have to have the Kelvin scale is because it starts at 0. When we talk about Charles' law on Friday, we're going to talk about a temperature-volume relationship. And when we get to zero, absolute zero, then our volume of the gas is zero. Okay? And then it gets bigger because, again, when that particle stops moving, now we're going to ignore the volume of the gas itself. But when we talk about a gas, its volume is the space that it occupies when it's moving. So, we can't have a negative degrees Celsius because that would give us a negative volume. And there's no such critter. You make a negative volume, you're going to be richer than rich. Okay? Just think about that. You can have negative volume. No more storage units. No more dirty rooms. No more, Think about it. The possibilities are unlimited. However, I'm yammering on. So, here's what you're going to be using, and sadly, you'll be given this. Okay? Because they give it to you in AP Chem. So, if they give it to you in AP Chem, I give it to you in here. And it's actually located right there. Yeah, I had to look for it. It's bigger than the rest of the font, so you just have to know how to use this calculation. So and here's some practice problems. We want to convert Kelvin into degrees Celsius. So how would we go about doing that? Subtract, yeah. So if we're looking for this, and we're given this, and we're looking for this, then that means we need to subtract 273 on both sides. Okay? Oh, 273. Again, it's given to you, so make sure you know how to use it. So in this case, we subtract 273. And what number do you get there? There you go. And that is degrees Celsius. And same thing here, subtract 273, negative 100. And if you need to use a calculator, that's fine. Look difficult? Well, the catch is now going from degrees Celsius to Kelvin. Now we use the actual calculation and add 273. So add 273. So now you got 373 Kelvin. Now the wacky thing about when you write Kelvin, it's not degrees Kelvin. But if you wrote a little zero there, I'll look at you funny for a while, but hopefully me looking at you funny for a while will make you change. But there is no degree sign on there. But if you put it on there, I'm sure you'll be all right. And then this one is like 649. Okay. There you go.
Later this week, he's going to
Yeah, later we'll actually use it in something. So, the homework. The ones